Welcome to our channel. Today, we're diving deep into one of the fundamental algorithms in machine learning, K Nearest Neighbours, or KNN. This algorithm is a cornerstone in data science, particularly when it comes to classification and regression tasks. By the end of this video, you'll understand how KNN works, see it in action with some example code, and grasp the differences between the brute force approach and an optimized KNN search. Let's start with a basic explanation of how KNN works. Imagine you have a data set with points plotted in space. Each point represents a sample, and each sample has features that determine its position in that space. When you receive a new sample, the goal is to determine which category it belongs to based on its proximity to other points in the dataset. Here's a step-by-step breakdown. Feature space. Every data point is represented in an n-dimensional space where each dimension corresponds to a feature of the data. Distance metric. Calculate the distance between the new sample and all existing samples in the dataset. Common metrics include Euclidean, Manhattan, and Hamming distances. K Neighbours. Identify the K closest points to the new sample. These are its nearest neighbors. Majority vote. For classification, the new sample is assigned the most common category among its K nearest neighbors. For regression, the value is the average of the K nearest neighbors. Now, let's dive into an example using a brute force approach first, and then we'll see how KNN handles the same scenario. This method involves calculating the distance from the query point to every other point in the dataset. While it's straightforward, it can be very slow for large datasets. First, let's import dependencies. We will use matplotlib for data visualization and numpy for numerical operations. Here we have some points plotted on a 2D plane. We are taking a small dataset for better understanding. And here I have plotted our data points using matplot library. We can see our data points on this scatter plot. Now, let's implement the brute force search. Let's take a sample point and find its 3 nearest neighbors using the brute force approach. In this code, we import the distance module from scipy.spatial to calculate Euclidean distances. We define our new sample point. In this for loop, we calculate the distance between the new sample and all other points in our dataset using the Euclidean function. Then we identify the indices of the 3 nearest neighbors using the argsort function from numpy. Finally, we are printing the indices and the neighbor data points. Let's run this cell. As we can see, it found 3 nearest neighbors 5, 5, 6, 5, and 4, 7. We can see in the plot our sample data point 4.5, 5.5 should lie over here, and these 3 points are found as nearest neighbors. This brute force method works well for small datasets, but as the size of our dataset grows, it becomes computationally expensive. Now, let's implement the KNN algorithm using an optimized approach. In this code, we import KNeighbours classifier from the neighbors subpackage of the scikit-learn library. This method is much faster, especially for large datasets. Here we create a KNN classifier object named KNN. The nNeighbours parameter specifies the number of nearest neighbors to consider for prediction. In this case, we set it to 3, meaning the model will use the 3 closest data points in the training data to classify the new sample. This line trains the KNN model using the fit method. It takes 2 arguments. Data points is the actual training data, assumed to be a 2D array where each row represents a data point and each column represents a feature. This second argument represents labels for the training data. Note that we use dummy labels since we're only interested in finding neighbors. However, since we are using zeros here, these labels are essentially ignored in this specific example. In real-world classification tasks, we would provide actual class labels for each data point and data points. We then predict the neighbors of our new sample point. First, we define a new data point, new sample, to predict its class. We then use the neighbors method to find the nearest neighbors of this new sample. New sample is a 1D array representing the new data point we want to classify. We reshape it to a 2D array with 1 row using reshape for consistency with the model's expectations. Return distance parameter tells the neighbors method to return only the indices of the nearest neighbors, not their distances. The neighbors variable now holds a list containing the indices of the 3 nearest neighbors in the data points array for the new sample. And finally, we print the indices of the nearest neighbors and the actual data points from the data points array using those indices. Let's run this cell. We see the data points that are closest to the new sample based on the train model. So, That is our KNN method. This method is significantly faster for large datasets. We will get a better idea by comparing the results of both approaches. So let's compare the performance of both approaches. This is a function to plot the datasets. To understand the efficiency, here is the time complexity function that simulates the time taken by both methods for various dataset sizes. This function generates random datasets of various sizes and measures the time taken for both brute force and KNN methods. Here we are simply calculating the time difference between the starting and ending time of the distance calculation. In case of KNN, we are again creating a classifier object with 3 neighbors, reshaping new sample for consistency, and fit the model with data points and zeros. In this for loop, we are calling the function for different dataset sizes, 1,000, 10,000, 1 lakh, and 1 million. Let's run this cell to compare the results. As we can see, as the dataset size increases, the brute force time significantly increases compared to the KNN time. This confirms that the brute force approach has a higher time complexity compared to KNN depending on the data structure used. It concludes that the brute force approach quickly becomes impractical as the dataset size increases, while KNN remains efficient. By understanding these differences, you can make informed decisions about which approach to use based on your dataset size and requirements. That's it for today's video. Thanks for watching, and don't forget to like and subscribe for more deep dives into machine learning algorithms. If you have any questions or topics you'd like us to cover next, leave a comment below. Until next time, happy coding!